speaker of the morning session is Borja Balle, and he's from Barcelona, visiting NYU on an extended stay. He's showing us some Linux script computation of LaTeX.
Thank you. So I'm going to present the joint work with my advisors in Barcelona, Jorge Castro and Ricard Gavaldà. And so the work is about learning Markovian models from time-evolving data streams. So I want to begin with a simple application, just to motivate the problem. And so the idea is, suppose you have an online store, like Amazon, for example, that gets maybe hundreds of thousands of queries per day from their customers. And if you want to build a model of your customers in order to make predictions about what are your customer preferences or what they will buy in the future, the traditional approach is that you store all the queries in a log, and then you run a pattern discovery algorithm or learning algorithm in this log to find a customer model. And what we would like to do is to do all this process in a stream fashion. And for one thing is because maybe the logs get very large and we don't want to store all of them. But also because what the customers want may change over time, and we want to be able to react to these changes. So this is a nice problem to think about it in a stream fashion. So a bit more formally, what I'm going to think about is that the items in my stream are strings. So in the example, the string is all the clicks that the user made. And I will make the assumption that all the items in the string are generated from a distribution, which may change over time, but strings are independent of each other. And so the task we want to solve is an unsupervised learning task. It's the task of learning this probability distribution from the streaming data. And we want to do that in a string fashion, in the sense that we want to process all the strings very fast, and we want to use a small memory profile. We will also want to be able to adapt to changes over time. And we want to produce models that can be used to make predictions or detect outliers or anything. But the goal here is unsupervised learning, so we don't fix what we'll use the models for. We only want to learn an accurate model of the process that generates the data. And the structure we propose is basically this one, where we have 4 blocks. One is a learning block, which will read data from the streams and produce hypotheses. And these hypotheses, there are some part of the hypothesis that can be adapted to changes in online, and that's what the adapter block does, this block here. But there are types of changes to which the hypothesis cannot adapt in an online fashion, and that's what the change detector is for. And if we detect this type of strong or abrupt changes, we will restart the learning procedure and produce a new hypothesis. And then there will be a predictor block that uses the hypothesis to make predictions, but I'm not going to talk about this block in this talk. So before I tell you how we're going to learn, I will tell you what we are going to learn. So what is our hypothesis class? And if you want to model a probability distribution over strings, what one would think, for me, the most natural example of this thing would be a hidden Markov model, and we're going to use a close relative to hidden Markov models, which are probabilistic automata, in particular probabilistic deterministic automata, which is basically, there's a DFA. I don't know, who doesn't know what a DFA is? Okay, so a DFA is a finite state machine, which has a finite number of states, and you assume that you have a finite alphabet. In this case, the alphabet is just 2 letters, A and B. And so from each state, you can have at most one outgoing arg labeled with each letter, and you also have one initial state, and you may have several stopping states, which are marking with this cross. In this example, there's only one stopping state. And once you have this finite state machine, you can add transition and stopping probabilities to it, which is like a probability distribution for each state. For example, for state 1, we can generate an A with probability 0.3, a B with probability 0.7, and a stop with probability 0. Once you have this table and the DFA, you can generate strings by starting in the first state and sampling from this distribution, deciding whether you generate an A and return to the same state, and then, for example, generate a B and go to this state, generate an A, stay here, generate a B, and, for example, stop. if you see one of these objects, that you can have 4 parameters that characterize the complexity of these objects, and that characterize how difficult to learn these objects are. And for these are the number of states, the size of the alphabet, the expected length of the strings generated by the machine, and a parameter which is called the distinguishability, that tells how different 2 states in the machine are. And this is important for learning, because if you have a machine that has 2 very similar states and you want to learn that machine, you will have to tell these states apart, and for that you will need a lot of samples. So in the example I showed you in the beginning, we could say that sigma is, so the sessions of the users will be a series of clicks on different web pages. So you can think of these as strings over an alphabet that contains all the possible pages in the website. For example, home, search, add to cart, checkout, and so on. And the reason why we choose PDFAs is because learning this type of objects in the pack learning sense is a well-studied problem. And I want to remark that when I talk about learning, I mean learning the structure and the probabilities, which is a much harder problem than just learning probabilities for a given DFA. And what is important, what we know that is important, is that any algorithm, we have a series of negative results that tells that any algorithm that can learn these things, its complexity must depend on all these 4 parameters I showed you. And there are several algorithms that work in this setting, and so most of them are work in a paradigm that calls state merging, which we can adapt. We show how to adapt to the streaming setting, but it's not straightforward because most of these algorithms do multiple passes and need to store the whole sample, which is something that we don't want to do. So just as an example, I'll show you how a state merging algorithm works. The idea is that you will create states, and when you find new states, you will decide whether this is really a new state or it's really a representation of a state you already have, and you have to do a merge. So that's what a state merging is. So at any time, you have a partial hypothesis, and you have safe states, which are drawn around here, and candidate states, which are drawn in a square here. And what you do is use your sample, or in the streaming setting, you would use like the new examples you get, to make statistical tests and decide, for example, if I have this candidate, I only have one safe, I have to decide whether this candidate is equals to this safe and do the merge, or if it's different, so I do a test and I get that it's different, so I decide to promote this to a new safe state. And to this new safe state, I will add a couple of candidates. Then, for example, I can consider this candidate and do the test, and it tells me that this candidate equals to the initial state. So I do the merge, and so on and so forth, and you can get in the end, you find the structure of a DFA, which is one part of the learning. The other part is estimating the probabilities, and this is easier. So in order to do that from streaming data, the first thing we want is, we don't want to store the whole sample, so we use the space-saving sketch, which just keeps track of the most probable strings, and this is enough if you want to do the mergings because of the definition of mu, which I don't want to get into. Another thing that's very different from the batch setting is that we do, so we have to decide when to make these tests, and we do this in an adaptive way, in the sense that we want to decide when to merge or when to promote one candidate state to a new safe as soon as possible, as soon as enough information is available, but without making too many errors. Another thing is that if you have a batch sample, you can train with different parameters of n and mu and cross-validate them, but you wouldn't like to do this in a streaming fashion. So you want to do the search, but not try all the parameters. So we have a way to do this fast. And the other thing, which is like one of the most interesting things, I think, in this kind of algorithms, is the core thing, that is, how do you do these statistical tests? And one thing you can do is, of course, base your tests in doing using a Heffding bound or Babner-Chervonenkis bounds. But the problem with this, as I'll show you in a minute, is that when you want to do a merge, this is very slow. So what we proposed is to do a bootstrapped confidence intervals in the streaming fashion, which is something we haven't found before. And in practice, this gives a faster convergence. And of course, we can bound the sample time and space complexity of our algorithm. And I think the most interesting thing is that we can process each string in time proportional to its length. And also that if we don't know these parameters, the memory used by the algorithm grows sublinearly in the length of the string. So t would be the number of elements read so far. So it would be like almost the square root of t, but you have a c here, which you can trade off. If you take a larger c, you get faster convergence, but your memory grows faster. And if you take a smaller c, your algorithm converges a little slower. So let me tell you a little bit more about this problem of testing similarity between probability distributions, which is at the core, the test we need to do in order for the learning. And basically the thing is you have two samples, S and S prime, that comes from distributions d and d prime. And you have to decide whether the distributions are the same or they are the distance larger than mu. And the basic idea, if you want to do that, what you could do is compute a confidence interval I that contains the true distance with high probability. And then if the lower bound of this interval is larger than 0, you decide that the distributions are different, because you know that with high probability the true distance is larger than 0. And otherwise, if your upper bound is lower than mu, you can decide that the distributions are the same. And if none of these occur, maybe it's because you do not have enough examples, so you wait until you get more examples. And the problem with this test is basically one of asymmetry, and it's that deciding dissimilarity is easier than deciding similarity. And you can see this very easily if you try to use the Hoving bound to get this interval of confidence. You'll see that the width of this interval goes to 0, like 1 over square root of the size of the sample. And if your samples are very far away, so their true distance is mu star and is quite larger than mu, you need 1 over mu squared examples, 1 over mu star squared. While if you, in order to say that two distributions are the same, you need 1 over mu squared, which may be way larger, much larger. And the problem is that to decide that two states are the same, you're always competing against the worst case, which is two states which are different, but just by distance of mu. So in order to improve a little bit the convergence so that we can make these merges faster, we propose to use bootstrap confidence intervals. So the basic idea of the bootstrap is that you will have several estimates of empirical estimates of the distance. Let's say we have R squared estimates and they are sorted. And taking quantiles in this empirical distribution, you can get a confidence interval for your parameter. And how do you do that in a streaming sense? So if you have a sample in the batch setting, the bootstrap would be, you have a sample of size n, you would sample with replacement another R samples of size n, and if you have one distribution, you will get R samples for one of the distributions d, R samples for d prime, and you can compute the distance, all the possible distances, which are R squared, between these two resamples. But of course, in order to do that, you need to store the whole sample. So if you don't want to store the whole sample, just assume that you're saving the information of the distribution into a sketch. What you could do to do the bootstrap in a streaming sense, in a streaming setup, is you have R sketches now, and whenever you see a new element in the stream, you take R copies of it and assign these copies randomly to the several sketches. And then all it happens is that the memory you were using, it gets multiplied by R, which you can take to be a constant. And the thing is that in theory you can prove that this asymptotically is no worse than Hoving. But more interestingly is that in practice, if you use like a good quantile for an upper bound, you see that this goes to 0 a little bit faster than what the Hoving bound gives you, so allows for faster convergence. And this is about the learning procedure, and now I'll talk a little bit just about how do you adapt to changes. So one thing is that once you have the structure, you have the DFA, you can estimate the probabilities from strings very easily. And you can also adapt these probabilities to change using, for example, a moving average. And this is the part that does the adapter block I showed you before. But sometimes there may be some changes for which the structure is no good anymore. And in order to detect that and restart the learning procedure for the structure, we need to see where the changes occurs. And the idea is that if you have some hypothesis class, you want to detect changes that are meaningful to your hypothesis class. There are some changes which your hypothesis class, thank you, will miss completely. So in this case, what we do is we take the structure without probabilities, and we keep an estimate of the expected number of times that a random string passes through each state. And you can keep a track of these estimates, and you can also detect changes using, for example, a sliding window technique. So whenever you detect a change, you're quite sure that the structure of the generating process has changed, and you can restart the learning. And of course, sometimes this can happen even when relearning the probabilities would be enough in order to adapt, but relearning the structure does no damage, because you can keep track of the probabilities while the learning process is running, and when the learning process terminates, you replace your old hypothesis. So we have done some experimental evaluation of this. We wrote the code with C++ and the Boost library, and we have just some preliminary evaluation with synthetic data, in particular the Rever Gramma, which is a well-known benchmark in grammatical inference. And I just want to show you here the comparison of the convergence and memory and time usage between the algorithm that uses the Hofding bound in order to test, or the bootstrap with R equal 10. And we see that the bootstrap converges 3 times faster. It uses around 10 times more memory, and the time processing per item is around 20 times more. So there's a loss in using the bootstrap in terms of efficiency and memory profile, but the algorithm converges faster, which is something, it's kind of what we expect. And just to wrap up, I'll tell you that, so as a future work, I'd like to integrate all these components I've shown you. I have separate codes for each of it in a whole system. It would be very interesting to try this with real data. And so one of the interesting parts is that real data has changes, but this is very difficult to deal with in synthetic data, or it's a difficult part, so doing real evaluations of this. One thing that our algorithm is not able to do yet is, if you see that there's a change in the structure, is recycle some part of the structure in the learning procedure so that you don't have to start again from zero. But this is an interesting algorithmic and statistical problem, which is quite challenging, I think. And of course, we'd like to see if we can apply this bootstrap on the streaming setting in another applications, which I think it's an interesting thing to try. Thank you.
Great, thank you. Time for a few questions. Somebody has to ask a question, or we're not getting lunch.
Come on.
No, that's not a valid question. So I was going to ask, do you have any ideas of real data streams you'd like to get your hands on?
So if I could get a handle on a web shop or I don't know. So we have a batch, a very large batch from a online travel agency, and I can run this there, but it's not enough. I mean, you can try to. One thing you can do is, if you have a very large real batch, you can learn a model from it and then use the model to generate data to try this. But still, the problem of how you generate artificial changes that are meaningful and that you can see really how the thing reacts to changes it's still not solved.
Have you given thought to trying to discretize sort of social discussions, like using a Twitter stream, and try to use that as a testing set?
No.
That might be interesting, because then of course you have some ground truth where you know that event happened, and you can see where the changes happened. You can see how the graph is reorganizing itself.
Yeah, actually that would be very interesting, but it would also take a lot of programming. So.
Sure. Okay. Yeah.
One suggestion for a data set where I think it's really useful is the finance data set.
Sorry, can you repeat?
Just using a finance data set. So in general, there are multiple modes in trading. You're looking at the trading of a stock. Many people have tried to look at when stocks trade in a mean reversion mode or a momentum mode, and to try and detect those kinds of regimes would be pretty interesting using a technique like this.
Yeah, well, can you tell me more offline, because I don't really know this data set. I'd be very interested. Thank you.
Okay, you now all deserve lunch. Let's thank our speaker again and all the speakers for attending. We will reconvene at 1:30.
And so the idea is, suppose you have an online store, like Amazon, for example, that gets maybe hundreds of thousands of queries per day from their customers. And if you want to build a model of your customers in order to make predictions about what are your customer preferences or what they will buy in the future, the traditional approach is that you store all the queries in a log, and then you run a pattern discovery algorithm or learning algorithm in this log to find a customer model. And what we would like to do is to do all this process in a stream fashion. And for one thing is because maybe the logs get very large and we don't want to store all of them. But also because what the customers want may change over time, and we want to be able to react to these changes. So it is a nice problem to think about it in a stream fashion. So a bit more formally, what I'm going to think about is that the items in my stream are strings. So in the example, the string is all the clicks that the user made. And I will make the assumption that all the items in the string are generated from a distribution, which may change over time, but strings are independent of each other. And so the task we want to solve is an unsupervised learning task. It's the task of learning this probability distribution from the streaming data. And we want to do that in a string fashion.
Our last speaker of the morning session is Borja Balle, and he's from Barcelona, visiting NYU on an extended stay. He's showing us on the next group computation of LaTeX.
Thank you. So I'm going to present a joint work with my advisors in Barcelona, Jorge Castro and Ricard Gavaldà. And so the work is about learning Markovian models from time-evolving data streams. So I want to begin with a simple application, just to motivate the problem. Changes in online, and that's what the adapter block does, this block here. But there are types of changes to which the hypothesis cannot adapt in an online fashion, and that's what the change detector is for. And if we detect this type of strong or abrupt changes, we will restart the learning procedure and produce a new hypothesis. And then there will be a predictor block that uses the hypothesis to make predictions. But I'm not going to talk about this block in this talk. So before I tell you how we're going to learn, I will tell you what we are going to learn. So what is our hypothesis class? And if you want to, in the sense that we want to process all the strings very fast, and we want to use a small memory profile. We will also want to be able to adapt to changes over time, and we want to produce models that can be used to make predictions or detect outliers or anything. But the goal here is unsupervised learning, so we don't fix what we'll use the models for. We only want to learn an accurate model of the process that generates the data. And the structure we propose is basically this one, where we have 4 blocks. One is a learning block, which will read data from the streams and produce hypotheses. And this hypothesis, there are some part of the hypothesis that can be adapted to